Here's an important illustration of a vector field that highlights some of the nuances in the theorem that we stated about conservative fields. And this is a familiar field to us. This is minus y over x squared plus y squared. And I have x over x squared plus y squared for my components. The region where this field is defined is what I'll call the punctured plane, just for discussion. And that's the real plane, but it's excluding the origin 0, 0, where these expressions are undefined. So just imagine the xy plane, and then I've just deleted the point at the origin. I've punctured it and put a hole there. M is minus y over x squared plus y squared. N is x over x squared plus y squared. And I'm going to test whether or not we think it's conservative by looking at the curl of the field. So remember, to do that, you calculate the partial derivatives with respect to the opposing variable. This case I need to do my. And if you do that carefully, it's quite a bit of work. You have to do the quotient rule and simplify. You'll get this expression here, y squared minus x squared up top, and my denominator got squared from the quotient rule. If you do the derivative of n with respect to x, it turns out you get exactly the same thing. It's not obvious until you do the calculation, but I'll leave that as an exercise for you. So what does this tell us? The curl of the vector field, which is the difference of these two partial derivatives, is 0 for all points on the punctured plane. Therefore, f is curl-free on the region. Now, we've seen this vector field before, and it's got a lot of swirling around the origin. And in fact, if I took a loop that goes around the origin, say the unit circle, and I go in this counterclockwise direction, we've done this calculation in class, and we saw that we got a non-zero amount of work. And so if you do, it doesn't matter the loop you take here, but if you do a loop around 0, 0, and you calculate the work done, you'll find that you'll get some non-zero value. Well, that's a problem for us because this tells us that the field is not conservative on the region. Yet the curl is equal to 0, and that seems contradictory to my theorem from before. What's going on here? How can I have a field that is not conservative but is curl-free? The problem in trying to apply the theorem that we discussed a moment ago is that the region R does not satisfy all the topological conditions that we discussed. In particular, the region R is not simply connected. The hole in the center here is a problem for us. A loop around the origin cannot be contracted down to a point without passing through the origin, and therefore it is not simply connected, and you shouldn't have applied the theorem in the first place. No guarantee that your field will be conservative if it's curl-free on a non-simply connected region.